This is Second Breakfast's Implicit and Mutation-Based Serialization Vulnerabilities in .NET. I'm Jonathan Birch. I hack Office from Microsoft. If you'd like to talk to me about this presentation or anything else security-related, please contact me on Mastodon. In this talk, I'm going to talk about various remote code execution vulnerabilities I found in .NET NoSQL engines. I'll describe what I'm calling a mutation-based serialization vulnerability. I'll tell you some ways you can bypass serialization binders, and I'll talk about how to defend against all of that. So what got me started on the research that led to this talk was last fall, I saw an article on a certain orange-colored website about LiteDB, which is a .NET NoSQL driver. And because this is apparently the sort of thing I do for fun now, I decided to do a security code review of their repo. When I did that, I saw this code. And what jumped out to me in this code was specifically this line, this call to type get type that's being passed a string. Now, to me, that's a really bad sign. But why is that a bad sign? So type get type in .NET is used to convert a string that's the name of a type into an actual .NET type object. And usually if you're doing that, what you're doing is you're taking some user-provided string and you're letting that string decide what type your application is going to make, what type of object. So you're probably doing some sort of marshalling, like you're writing your own custom serializer, or you're doing something sketchy with reflection invokes. And in general, all of this is a bad idea. All of this is about on par with writing your own cryptography algorithms or something like that. And what it means is if someone malicious comes along, they're sending you bad types, which means they're sending you bad code, and you're having a bad time. So what is LiteDB doing with this? LiteDB is a NoSQL engine. And the way you end up using it with .NET is your application says to LiteDB, I just want to store this object with this key. And LiteDB takes that object and it serializes it with a serializer they call BSON mapper into a BSON stream, which it stores in a file. Later on, when you want to get that object back from the database, it's going to take that BSON again and deserialize it with BSON mapper back into an object for you. So BSON is just a binary encoding of JSON. So you can look at it as JSON. And if you look at the LiteDB files, decode the BSON into JSON, it looks sort of like this. And if you look at this JSON, there's this underscore type key in it. And then there's just the name of a .NET type. And so what's happening here is when LiteDB is converting that BSON back into a .NET object, it's calling type get type on that type string. And that's how it's making it back into an object. So the stream is telling it what types to make. And that means this is just a polymorphic serializer. And that means you have all of the problems you have with polymorphic serializers. But well, what are those? So I'll give a little background now on .NET serialization vulnerabilities. In general, the way .NET serialization vulnerabilities happen is you've got self-describing data. You've got some box of data that's telling you what type it wants to be. So in this case, you've got a box that says it's a cat. When you deserialize that, your serializer says, well, it says it's a cat. I should make a cat object. You get a cat. And the problem is if someone malicious comes along and gives you a box that's labeled pain, well, then your serializer says, well, I guess I should make some pain, and you're having a bad time. If you want a little bit more information on this sort of low-level issues with .NET serialization, I suggest looking at the Friday the 13th JSON talks from Black Hat 17. But in general, the problem here is that if anyone can tell you what types you're going to make, there's types where if you create them and set their properties, they have side effects that maybe further an exploit. They're going to do things that you maybe don't want your application to do. Those are called gadgets. And here's a couple of examples. So assembly installer is a type in .NET where if you set its path property, it just calls load library on that path. So if you've been able to put a malicious DLL somewhere that the application can see, you've got code injection. Also, it's worth noting that assembly installer, if you give it an HTTP URL, will make a request and download that DLL. It won't load it. But you can still use this to get a ping back, which is sometimes useful. There's also object data provider, which is sort of the classic .NET serialization gadget. It's got properties on it that if you set those properties, you can call any static method on any type with whatever string and integer parameters you want. And people usually use this to call process.start just to pivot to shell injection. So, OK, that's how .NET serialization vulnerabilities work. Now I'm going to go back to LiteDB and what I'm calling an implicit serialization vulnerability. So here's an RCE payload for LiteDB. So here's some JSON. And if you look at this JSON, it's got that underscore type key again, which is the data telling you what type it wants to be. In this case, it's going to be an object data provider. That's that gadget that lets you call any static method. This is calling process.start. It's going to launch calc, sort of standard exploit thing to do. And all I'm going to do with this JSON here is convert it into Beeson and then deserialize it with LiteDB's Beeson mapper. And that's enough to run the code and launch calc. Now, it's worth noting here that when you use Beeson mapper to deserialize a stream, you tell it what type you expect, and it doesn't matter. LiteDB will go and make a type of whatever the data says it should be, set its properties, and it'll try to do a cast afterwards that'll fail, but it doesn't matter because the exploit has already run at that point. So if you remember how LiteDB works, it uses Beeson mapper to read its own storage. So I showed you that putting bad data in the Beeson mapper gives you RCE, which means that anything that puts bad data in that database file also gives you RCE. And the client using LiteDB probably doesn't know it's using a serializer at all. The client just says to LiteDB, store this object or give me the object at that index. So this is sort of an implicit serialization vulnerability. The client's not using a serializer directly. It's using a library that uses a serializer that it probably doesn't know about, but that makes that client vulnerable in lots of ways. One of them is if you just give it a bad database file. So LiteDB stores its database in a local file. If you go and look, there's lots of applications out there that use LiteDB just to store documents or game saves. So anyone who gives you a malicious file that's read with LiteDB gets RCE. LiteDB is also a NoSQL engine. It has queries. If you can get query injection against it, you can put malicious data into the database, and when that data is read, you get RCE. And there's one other method I found to get RCE against LiteDB that I will come back to. So what do you do when you find a remote code execution vulnerability in an open source library? Well, you go look at all of the other similar libraries and find the same vulnerability. So here's the same vulnerability in MongoDB. So here we have, again, some JSON. Here's that JSON telling you what type it wants to be. MongoDB uses this _t as this type specifier. Again, as an object data provider. It's going to call process.start to launch calc. And once again, all we're going to do is convert that JSON into Beeson and deserialize it with MongoDB's Beeson serializer. Now, it's important to note here that the type that you pass to the deserialize here does matter. MongoDB, before it creates the object, will check that it's assignable to the type that you're expecting. And if it's not, it won't create it. That means to exploit this, you've got to have something in the expected object graph that's open-ended, either a member of type object or an interface type, because in general, there's a serialization gadget you can force into pretty much any interface type that exists. So because MongoDB, again, is using Beeson serializer to read its own database, you have these same implicit serialization vulnerabilities. Any attacker who can write malicious data to the database that you're going to read can potentially get RCE if you're also reading something open-ended from the database. Now, it's important to note that I was only able to exploit this for the .NET driver. I don't know for sure that the Java and Python drivers are safe. I looked at them a little bit and couldn't find an exploit. But if you want to take a look at it, that might be worthwhile. So that's 2 NoSQL engines that I looked at. And here's a third. So here's an RCE payload for RavenDB. Again, you've got some JSON. It's telling you what type it wants to be with, in this case, a $type as the type specifier. It's going to make a Windows identity object. Windows identity is a JSON.NET serialization gadget. I suggest looking it up on Why So Serial, but in general, it's going to let you pivot to a binary formatter payload, which then you get RCE with. And what we're going to do with this JSON is we're just going to make a put request to the database server and just store it directly in the database that way. RavenDB allows reading and writing the database both as JSON and as objects. So if you write the JSON to the database that's malicious and then read it as an object, that's RCE. And in this case, again, we've got a bad serializer being used to read the storage. In this case, it's JSON.NET with unsafe settings. So RavenDB also has implicit serialization issues. If you can write malicious data to the database that someone reads, that's exploitable. If you can do query injection against a database and get malicious data in there, it's exploitable. And that special attack I mentioned that works against LiteDB works here too. Although, like MongoDB, RavenDB has a good assignability check, so your exploit has to somehow fit into the expected object graph. So, OK, that's 3 NoSQL database engines, but NoSQL is used in other ways too. So here's an RCE exploit against ServiceStack.Redis. ServiceStack.Redis is a NoSQL interface for a Redis cache. And here again, we've got some JSON. It's telling you what type it wants to be. It's an assembly installer here, so when we set this path It's going to call load library on that path. We'll just say there's a malicious DLL you've planted there. And what you're going to do to exploit ServiceStack.Redis is you're going to write the JSON to the database as a string and then read it back as an object. And that's sufficient to get RCE with it. So if you can inject into the cache and then get it read as an object, you've got RCE. And once again, the type that you're expecting when you read from the cache matters here. There's, again, a robust assignability check. So you have to, again, have something open-ended in the expected object graph. This still gives you implicit serialization issues. So if you can write to the cache and then it gets read later, you've probably got RCE. And that extra pattern I mentioned for LiteDB and RavenDB also works for ServiceStack.Redis. And now I'll get into that extra pattern a bit. So there was one other NoSQL engine I looked at that I had a lot more trouble with, and that was MartenDB. So MartenDB is a NoSQL interface for Postgres. And like RavenDB, it uses JSON.NET with unsafe settings to read its own storage. But it doesn't just let you write JSON to the database. Instead, you have to write objects to the database to read them. And when I was trying to exploit this, I couldn't find a way that it would let me do it, put an exploit gadget in there. It would always choke somehow when I tried to. And then I discovered a different way to attack it. And that leads into what I'm calling a serialization mutation attack. So here's an RCE attack against MartenDB. What I'm going to do here is I'm going to create a dictionary of string, and then I'm going to put two entries in it. The first one, the key is named $type, and the value is going to be, in this case, a type name for the workflow designer.net type. That's, again, a JSON.NET serialization gadget. Look it up on why so serial. But it lets you do an arbitrary XAML read. And then I'm going to put that XAML in the second entry. So I'm setting another property on it, which is going to be the XAML that's going to launch calc. And then what we do is we write it to the database and then later read it from the database. And that gets us RCE. That's all you've got to do is just write that dictionary to the database and then read it back. And that's a little bit weird. Why does that work? Well, MartenDB uses JSON.NET for its serialization. So this vulnerability actually comes from JSON.NET. Let's look at how it works there. Say you're just serializing a dictionary of string to string in JSON.NET. And you've got this fruit key and this pair value. Well, JSON.NET just uses the keys in your dictionary directly for the JSON it produces. So you end up with JSON that also has a key with fruit and a value named pair. Now, if you compare that to what a serialization exploit payload looks like for JSON.NET, like this one, you've got that $type, which is the type specifier, and then you've got the type name you want to use, in this case assembly installer, and then you set some properties, and you've got RCE. And the key trick here with this is that that $type key isn't special. Nothing prevents you from putting $type in a string-string dictionary as a key. And also, it turns out JSON.NET doesn't take it out if you serialize that dictionary. So if you serialize that dictionary, $type goes into the JSON it produces. And then when that gets deserialized later, that's the type of object it's going to become. So with JSON.NET, you can just serialize a dictionary string-string, say, well, there's a key named $type, put a type name in there. And when it gets serialized and then deserialized unsafely, it mutates into something else, and you can get RCE out of it. This works with a lot of other key value storage types like hash table, JObject, expando object, a bunch of others that are less common. And this sort of attack enables a lot of attack patterns that were previously believed to not be possible. So say you've got a website where you can enter some key value data. This is a screenshot from a certain website that lets you enter key value data that was not exploitable with this attack. But you can enter some key value data into a web form somewhere. You do a form post on a web front end somewhere, it becomes a dictionary or a hash table. And let's say at some later time, that dictionary or hash table gets serialized to a cache or a database. And at some point later on, it gets deserialized from that cache or database. Well, if you're using an unsafe serializer or a serializer with unsafe settings, you can put key value information in there so that when that serialization happens, the object that comes out of the cache is something else. It's mutated into some sort of exploit gadget. And this means that you can attack serialization even though you're never touching the serialized data. You may not even know for sure that serialization happens. You can do this just blindly. And this is that extra attack pattern I was mentioning for those NoSQL engines earlier. So here's a mutation attack against LiteDB. I'm going to make a dictionary of string to string. I'm going to put a couple entries in it. One's got a key of _type. It's going to be an assembly installer. And I'm going to set the path property on it just by setting another key value pair in the dictionary. And for LiteDB, if you just stick that in a database and then read it back, it's RCE. Remember, LiteDB didn't used to check assignability in 5.0.12. So it didn't matter where this was in a data structure. It didn't matter what it was expecting. If you controlled a couple key value pairs in a dictionary that would get written to the database and read back, that was enough for RCE. This is kind of a ridiculous bug, honestly. Like, this was really easy to exploit for a lot of applications. And it turns out a lot of .NET serializers have this issue. So here's a table of all the ones I know of. They're all JSON and BSON serializers. There's different conditions on these that make them harder or easier to exploit. It's worth noting I couldn't make this work with MongoDB. I won't promise you can't do it, but I couldn't do it. And this is kind of a tricky exploit. For a lot of serializers, you can sometimes pull this off if everything lines up right. Like for JSON.NET, you have to have unsafe serialization settings, like a bad type name handling value. You have to be serializing things in such a way that JSON.NET doesn't double up the type specifier. You really just need to experiment with that to figure it out. And you have to have that pattern of serializing and the deserializing somewhere. But for some serializers, this is really easy. So if you're using JavaScriptSerializer with a simple type resolver, for example, it will just make it work. It doesn't matter if you control the first key value pair. It doesn't matter what types were expected. It will go out of its way to make this attack work. So some cases are hard to exploit. Some are really easy. You can defend against these attacks, and the best way to do that is to not use a polymorphic serializer. Don't use a serializer where the data gets to tell you what type you're going to make from it. JSON Serializer in .NET is actually pretty good for this. You can also use a serialization binder, because when that mutation happens, the binder will still get asked about the type that's being created, even though it's not the type that you serialized in the first place. But I'm not going to tell you how to bypass serialization binders, so grain of salt there. So how to bypass serialization binders? So if you're using a serialization binder for security purposes, what you're usually doing is using it as a sort of filter. You're saying, OK, my data is telling me to make some types, but I only want to make a certain set of types. These are the ones I expect. So I'm going to have an allow list that says, well, if it's one of these types I expect, I'll make it. Otherwise, I'll throw an exception. If you're doing it like I just described right there, it works pretty solidly. That'll keep you from making that pain or those exploit gadgets that I've been talking about. And so if you're doing it right, it looks about like this. This is a good serialization binder. This is just a strict allow list of assemblies and types together. And you want to do a string-string match and throw an exception if it's not something you expect. And if you do it like that, it works OK. I don't know what way to bypass it. But that's often not what people do. Instead, a lot of times what you see is something more like this. This serialization binder is saying essentially, well, there's an assembly I've made. I know it doesn't have bad types in it. I want to be able to serialize everything in it. So we'll just say, if it comes from my trusted assembly, it's OK. And I'll just call type getType to actually get the type once I know it's from my assembly. And the problem is, what if your trusted assembly has a type like this? So this is a type. It's initialized list we're going to invent here, which just inherits from the generic list type in .NET and has an extra property. This looks pretty harmless. But if this is in your trusted assembly, well, you've got RCE because you can bypass that binder. And the trick for that is you can make a payload like this. So this is the payload for that initialized list again. And the $type parameter on this says we're just making an initialized list, and that's the only thing your binder gets asked about. And that initialized list type comes from your assembly, so that works. The type inside of the template for that generic is assembly installer. That's a serialization gadget. But your serialization binder won't get asked about that if you don't specify it. And the serializer can still figure out it needs to make one of those when it deserializes this values section. It'll make this anyway. It won't ask your binder about it, so that'll bypass your binder. So you shouldn't make a serialization binder that just allow lists assemblies. Another trick you can use to bypass serialization binders is what I'm calling contagion. So I was just explaining that only the types directly specified by that type specifier go to the binder. But generally, when you're serializing or deserializing types, there's a lot of properties in there that have their own types. And you can specify them in the payload, but you don't have to. And if you don't, the serializer will figure it out for the most part during deserialization. So if there's some serialization gadget out there and it's a member of some other type, you can actually get to that gadget just by serializing that other type and setting that member property of it. And that chains. So if you've got a gadget that's a member of a member of a member of a member of some type, you can get to it that way too. So here's a specific example. The Windows identity type I used earlier, it's a serialization RCE gadget for JSON.NET. And let's say you've got a serialization binder where you're just block listing that type. You're saying we're not going to allow that. Well, there's other types you can use to get to that type anyway. In particular, there's this Windows authentication event args type, which has a constructor argument called identity, which has the type Windows identity. So what you can do is you can serialize that authentication event args type, and the only type your binder gets asked about is that. But when that identity argument gets deserialized, well, JSON.NET will still go ahead and make a Windows identity object. You can set its properties there, but your binder doesn't get asked. So this is another way you can bypass serialization binders. OK, so that's a lot of problems. What if this has been fixed? So I talked to all of the vendors for all of those NoSQL engines, mostly last year in January and February this year. And everyone but MartenDB has made a fix. The fix in MongoDB is pretty solid. They added a strict allow list for the types that can be created during deserialization. I haven't found a way to bypass it. Everybody else that made a fix pretty much just added a block list and added an assignability check. And I just showed you that block lists really don't work. And in fact, I can bypass all of those other fixes. And I've told all of these vendors, hey, I can bypass your fix, and they're not fixing it further. So all those other NoSQL engines, you can still get RCE against if you can write untrusted data to the database that somehow gets read later. Now, as far as the mutation attacks, so JSON.NET has mutation, and they're not going to fix it. I talked to James Newton King about it. He said that's what it's supposed to do, more or less. And so there's not going to be any changes there. If you're using JSON.NET, you need to worry about mutation. Similarly, JavaScript Serializer in .NET will not be fixed. The .NET folks told me essentially, don't use JavaScript Serializer. We tell people not to use it. Also, don't use simple type resolver. We tell people not to use it. So there's no fixes that are going to be made there either. OK, so that's a lot of stuff. That's kind of problematic. What are some best practices to defend against all of this? So don't use polymorphic serializers. Don't use a serializer where the data gets to tell you what type it's going to be. Don't call type get type. In Java, don't call class.forName. Don't use type resolvers that sort of do this sort of thing for you. In general, there's lots of patterns where you're accidentally making a serializer. Just try to stay away from all of them. And remember that because of mutation attacks, you can't use an unsafe serializer even on the back end where nobody can see it, because a lot of times it can still be attacked. You can even attack like deep object copying sometimes with mutation and still get RCE, even though no one knows the serialization is happening necessarily, unless you're doing sort of blind injection attacks. And this one kind of hurts, but don't read untrusted data from NoSQL. MongoDB is probably OK. But most .NET NoSQL engines, you can still get RCE if you can write bad data to the database and then someone later reads it. This pattern is probably there for lots of NoSQL engines that aren't in .NET also. In general, anything that's got the property where you can just give it an object to store and then later get it back, there's going to be a serializer there. And if that can be any type at all, it's going to be a polymorphic serializer, and you probably have the same vulnerability. If someone wants a good security research project, look at this in Java or Python or whatever other framework you want to. I didn't really. And don't use serialization binders. Like, if you do it just right, it can work. But I've seen this done wrong so many times that anymore I don't think people can generally write a good one. You're better off trying to actually architect your application so that you never need a serialization binder in the first place. Takeaways from this. Reading untrusted data from NoSQL is probably a vulnerability. Because mutation attacks are a thing, you can't use unsafe serialization even in cases where the serialized data can't be modified. That includes not just serialization that happens only on the back end, but like putting an HMAC on the data doesn't prevent mutation attacks either. And serialization binders are usually vulnerable to bypass. And that is my talk. I'll be in the wrap room after this also, and the meetup lounge from 5 to 5:30 this evening. But I have a little time for questions now, if anyone has one.